Hello, good afternoon, everyone. Thank you for attending my APS March Meeting 2024 talk. My name is Matt Wilson. I'm a graduate student from Joshua Louis' lab at UC Riverside. And today I'm excited to talk to you about our recent discovery of bipolar Wigner crystals and valley-dependent exciton Umklapp scattering in monolayer WSe2, tungsten diselenide. And I will begin by explaining what a Wigner crystal is. So charges that I simply represent here by black dots on the left are in an electron gas state when their interaction energy is much less than the kinetic energy. But if we reduce the kinetic energy enough so that the interaction energy term begins to dominate, spontaneous long-range ordering due to Coulombic interaction occurs and a Wigner crystal is now formed here. I add lines in between the charges' 6 nearest neighbors to make it apparent that the Wigner crystal has a triangular lattice. And despite being theorized nearly a century ago by Professor Eugene Wigner, there is still a lot to discover about the properties of the Wigner crystal state because historically experiments have required ultra-clean samples, ultra-low temperatures, usually less than 1 Kelvin, and high stabilizing magnetic fields. What we are now seeing is transition metal dichalcogenides are excellent candidates to hold Wigner crystal states. They can, of course, be mechanically exfoliated down to a few or single unit cell layers, which increases the strength of interactions due to quantum confinement. And their charge carriers have relatively high effective mass at about 40% of the free electron mass. And so a high effective mass and high interaction strength makes a once extremely fragile state more robust, allowing us to see the Wigner crystal state at higher temperatures and without the assistance of magnetic fields. Our devices take that monolayer WSe2 and via the dry transfer stamp method, encapsulate this WSe2 in insulating HBN hexagonal boron nitride layers. And the TMD is electrically contacted and gated through graphite, which allows us to inject carriers into the TMD by simply changing the gate voltage here. And now here I show a reflection contrast map that we took of our monolayer WSe2 device at 35 Kelvin and with 0 magnetic field. This reflection contrast map is a function of collected photon energy and gate voltage, where positive voltage indicates electron injection and a negative voltage indicates hole injection. And so if we focus on the area near to the neutral exciton resonance here, and we take a second derivative with respect to energy, we notice some interesting new features here. These two blue lines that come from the charge neutrality point of the neutral exciton shows us that we have Wigner crystal formation in both the electron and the hole side here. And you can see that this Wigner crystal is continuously tunable between electron and hole side, and this is why we actually call it a bipolar Wigner crystal. Now, allow me to explain how we know these lines are the optical evidence of Wigner crystal formation. So the physical mechanism that causes these lines in our data is exciton Umklapp scattering due to the zone folding effect caused by the additional crystalline periodicity of the Wigner crystal. So to further explain this, if we add a Wigner crystal to the exciton's environment, shown on the left here, the added periodicity again causes a zone folding effect that modifies the originally parabolic band, this blue one here, and it adjusts it in such a way that the surrounding gray bands, they are acting more as a pictorial way of representing zone folding, but in reality, the Brin-1 zone is being folded back at the momentum values where the gray and the blue parabolas intersect. And this momentum value here is inversely proportional to the lattice constant of the Wigner crystal. And what this shows is the formation of a new optically resonant state that maintains exciton 0 center of mass momentum, where this orange arrow is now. Exciton Umklapp scattering into this new state can occur, which increases the energy of the exciton by the length of this orange arrow. And so now if we proceed from a low density Wigner crystal to a high density Wigner crystal state, we see that the Umklapp scattering energy increases as the bands move further away due to the increase in the density of the Wigner crystal, which decreases the lattice size of the Wigner crystal. So to simply put all of that, the blue lines we see in the data are as a result of Exciton Umklapp scattering, which is the optical evidence of a Wigner crystal, and the value of the energy separation from the neutral exciton is proportional to the Wigner crystal density. So now let us see how the Umklapp scattering intensity is affected by increasing the system temperature. And we can start from 5 Kelvin, as I've already shown you the 3.5 Kelvin data. And of course, at 5 Kelvin, the data remains strong. 10 Kelvin, 15 Kelvin. And at 20 Kelvin, you can just barely see the whole side signal still existing, and this is where the electron side starts to dissipate quite heavily as well. At 25, I would argue that the whole side is completely gone at this point, and the electron side is still barely visible. And then finally, at 30 Kelvin, all signal is lost into the background. And so, of course, if we take line cuts for each temperature along this dotted line here, we can have a more qualitative analysis of the melting temperatures. So we extract the intensity under the curves for those temperature line cuts along the entirety of the Umklapp scattering signal and integrate to give us this plot here, where the green squares are the electron side data and the purple circles are the whole side data. And linear fits show us that the electron side Wigner crystal melts at about 27 Kelvin without the need for any magnetic field, and the whole side Wigner crystal melts at about 22 Kelvin, once again without any requirement of magnetic field. And so these temperatures are quite a bit higher than the usual melting temperature of a Wigner crystal, which is often in the millikelvin range when not housed within TMDs. So again, just to emphasize, all of the previous data was collected without the application of a magnetic field, meaning that the K and the K prime values were degenerate. And here I show the K and the K prime value bands using a color to indicate spin. Blue is spin down, orange is spin up. And due to the value degeneracy, tuning the Fermi level will distribute charges evenly amongst both values on, of course, either side of the band gap here. But now if we apply an out-of-plane magnetic field to our device, there will, of course, be Zeeman shifting of these bands. The magnetic field shifts the K and the K prime values up and down respectively due to the contribution of spin, atomic orbit, and Berry curvature to the magnetic coupling of each individual band, leaving us with a band structure that looks like this after Zeeman shifting. And of course, now, if we raise the Fermi level on the electron side, we can selectively fill only the K prime side conduction band, forcing the formation of an electron Wigner crystal with electrons that are only in the K prime value. We can do the exact same thing on the whole side to form a hole-based Wigner crystal in the K value. And we, of course, can selectively analyze these values by exciting and collecting with only a single helicity of light. If we excite with left-handed polarized light, we can create an exciton in the K prime value so that the electron in a hole had the same spin in WSe2. And we can excite instead with right circularly polarized light to form an exciton in the K value. And so all of this together enables us to have a value selective Wigner crystal and exciton formation. And so here I present the left-handed light map, which shows us the K prime value behavior. Again, we see Umklapp scattering on both sides of the map. And on the electron side, we have what we are calling case 1, where we have selectively placed a Wigner crystal in the K prime value, where the exciton is also formed. But once again, it's important to note that the bright exciton in this case has a different spin than the Wigner crystal, right? Here it sits on the blue bands, and the Wigner crystal in this case is orange. So in this case, there is no phase-space overlap, which is why we see actually weak scattering in the plot here. And on the whole side of the K prime value map, we have case 2, where we now have a Wigner crystal in the opposite valley of the K prime exciton. So once again, of course, there is little interaction here, so we have weak scattering strength in our map as well. And so now if we switch the optical helicity of light to reveal a map of the K valley, and if we start on the electron side, we once again now have case 3. And just as before, the electrons that form the Wigner crystal are in the K prime valley, but now our exciton is located in the K valley. So there is no strong scattering, which is obvious from the very low intensity that we see here in our map. And then finally, we have case 4, which is by far the most interesting case due to the strong scattering signal that we do see here. The Wigner crystal and the exciton are located in the same valley, and they have the same spin, so that there is a phase-space overlap between the two. And it is this phase-space overlap that affects the Umklapp scattering strength tremendously, leading to this strong signal that we see. And here I gather all 4 of the cases together in a sort of a summary. And of course, cases 1 through 4 all interact with the Wigner crystal via direct Coulombic interaction. But because the electron and hole are of opposite charges, the exciton is charge neutral, so any Coulombic interaction that one charge carrier feels is canceled by the Coulombic interaction of the opposite charge, leading to a weak scattering. Case 4, however, is unique from the other cases because we have an additional scattering term due to the simultaneous spin and valley overlap of the exciton and the whole Wigner crystal in the K valley. And so this additional mechanism, which is stated here in red, is the long-range exchange interaction, which is sizable only in case 4 because the hole in the exciton is interacting with identical holes that comprise the Wigner crystal. And so there is some Pauli exclusion between the exciton and the whole Wigner crystal. And so this is why we see strong scattering in this case, case 4 only. And so taking this additional scattering term due to the phase-space overlap in case 4 into account leads our theory collaborator, Dr. WSe2 from Taiwan, to simple calculations of Umklapp scattering probability, which is proportional to signal strength, with charge density here on the lower axis. And these Umklapp scattering probabilities match our experiments very well, in that case 4's scattering probability is consistently larger than the next nearest case. And the remaining 3 cases here are very similar in scattering strength and significantly lower than case 4. And so to quickly summarize, Monolayer WSe2 shows excitonic signatures of electron and hole Wigner crystals. We demonstrated that the Wigner crystal has a high thermal stability, up to 27 Kelvin on the electron side and 22 Kelvin on the hole side. And we see excitons exhibit value-dependent Umklapp scattering with Wigner crystals, where I discussed the 4 possible cases that we have under a magnetic field. And we showed that case 4 shows the largest scattering due to the long-range interaction term. And so there is a lot more for us to learn about Wigner crystals, and we are continuing to refine our theories as well. I'm now happy to take questions. Thank you.